Good morning, all participants. Madam, please तुम्ही mute करा, madam. Priyanka, madam. Good morning, all participants. I'm Dr. Sabre. I welcome all of you in this national webinar on fractional calculus and dynamical systems, which is organized by Department of Mathematics, Statistics, and Internal Quality Assurance Cell of Jaysingpur College, Jaysingpur. I heartily welcome today's resource person, Dr. Kishore Kuche sir, Assistant Professor, Department of Mathematics, Shivaji University, Kolhapur, and another resource person, Dr. Sachin Kumar Bhalekar, Associate Professor, School of Mathematics and Statistics, University of Hyderabad. Now, I request Dr. Ramesh Shinde sir to introduce today's webinar topic. Shinde sir, please welcome.
Good morning, all of you. I heartily welcome you all from behalf of IQAC Jaysingpur College, Jaysingpur, and Department of Mathematics and Statistics on the occasion of national level webinar on fractional calculus and dynamical systems. The main purpose of this webinar is to give ideas to the students, researchers, and faculty members in mathematics around the corner of India on fractional calculus and dynamical systems. To serve this purpose, we have two resource persons. The one, Dr. Kishore Kuche sir, Department of Mathematics, Shivaji University, Kolhapur, and the second one, Dr. Sachin Kumar Bhalekar sir from University of Hyderabad. Before I stop, let me tell a few things about our college. Our college is A grade accredited by NAC Bangalore, and our college also have DST FIST sponsored level 1 and have many instrumental research facilities. So let me request Mr. Preetham Patil sir to introduce our first resource person, Dr. Kuche sir from Shivaji University. Mr. Preetham Patil sir, please.
Good morning and welcome one and all. Firstly, I thanks organizer for giving me opportunity to introduce today's eminent speaker, Dr. Kishore D. Kuche sir. It's my pleasure and great honor to introduce an amazing personality, Dr. Kishore Kuche sir. Actually, he has very rich CV, but due to restriction of time, I'll introduce in brief. He is working as an assistant professor in Shivaji University, Kolhapur. He has very wide teaching experience of 19 years, out of which he taught 6 years at UG level, and he has been teaching since last 13 years at PG level, that is Mathematics Department, Shivaji University. His research interest includes fractional differential equation, abstract differential equations, integral inequalities. He has 32 research publications in reputed journals like SCI, WOS, and Scopus. He has research collaboration with several prominent universities in Brazil, China, and Spain also. It is notable that Sir got research grant from Science and Engineering Research Board and UGC for 2 research projects. Name of first research project is Analysis of High-Hilbert Fractional Differential Equation. and amount sanctioned for it is 17,58,000. And name of second research project is on nonlinear mixed fractional integral differential equation in Banach space, for which amount sanction is 1,97,000. Actually, it is impossible to mention his every single accomplishment because they are lot. He delivered invited talk in several national conferences and international conference in USA also. He presented number of papers in national as well as international conferences. One student is awarded with PhD and 3 students are working under guidance of Dr. Kishore Kuchesar. He, he is author and co-author of many engineering and higher mathematics books. Dr. Kishore Kuchesar worked as organizer of various UGC sub and UGC DST sponsored national seminars and workshops. He is a member of numerous research committees and academic bodies. It is such an honor for us to have such personality between us. So please welcome Dr. Kishore D. Kuchesar.
Thank you very much for your nice word. I will start my lecture. His screen is
Yes, sir.
visible
Yes,
to
sir.
all?
Yes, sir. It's visible, sir. No problem.
Okay, just a minute. Thank you very much. Good morning to one and all. I'm happy to deliver a talk on basics of fractional calculus in the national webinar on fractional calculus and dynamical system. Though there may be many participants, I am not claiming for the material of this slide. My total presentation is based on the 2 books, one by Igor Podlumny and another by Kai Dithel. Outline of my talk will be like this. What is fractional calculus? History and development. Properties of most widely used definition of fractional differentiation, that is Riemann-Liouville fractional derivative and Caputo fractional derivative. We will see Laplace transform of fractional derivative. We'll make the comparison between Riemann-Liouville derivative and Caputo derivative, and we will have an overlook on Mittag-Leffler function. Dear friend, we know the concept of first order derivative, second order derivative, nth order derivative. Similarly, we know the concept of first integral, double integral, n-fold integral of a function where n is natural number. Now, idea is to generalize the notation of differentiation and integration of integer order to that of arbitrary order, that is real or complex. The fractional calculus is the branch that deals with the integral and derivatives of arbitrary order. We will discuss derivative and integral of real order in this presentation. This is called fractional integrals and fractional derivative, which unifies and generalizes the integer order differentiation and n-fold integration. So we'll start with the history of fractional calculus. The origin of fractional calculus can be traced back in the 17th century when Newton and Leibniz was working on calculus of differentiation and integration. At the time, Leibniz introduced this symbol, nth order derivative of f of t when n is natural number, and he reported to the mathematician L. Opita by the later. And Opita replied him, what about when I will take n is equal to half in this definition of nth order derivative. At that time, Leibniz replied that it will be lead paradox from which one day useful consequences will be drawn. And we can see that in last 2 to 3 decades, there is a lot of research many physical phenomena can be suitably modeled with the help of by Leibniz to LOP in 95. Therefore, this 13th September is considered as the birthday of fractional calculus. There are many definitions of fractional derivatives. In generally, these definitions are not coincides with each other. Possibly, this may be due to that many authors would like to present different properties of the classical integer order derivative. If you are generalizing any concept, we must get the particular case, the realistic case. Okay, so these are the list of the fractional order derivatives. These are new classical fractional derivatives: Grunow-Lyapunov, Sonin-Lyapunov, Liouville derivative, Riemann-Liouville derivative, Caputo derivative, and so on up to Edley-Kober fractional derivative. In last decade, new fractional derivatives has been introduced by Machado derivative, Chen-Masto derivative, Coimbra derivative, Cartan-Polar derivative, and recently two derivative has been introduced in 2018. One is Sai-Hilbert fractional derivative and another is the Attanganapa-Bellino fractional derivative. So review has been given in the research paper, but I will not go for that. Already I have discussed that when we are generalizing any concept, it must give your classical concept as a particular case. Okay, so if you are defining the fractional order derivative of any order, say real order, okay, when I replace real order by a natural order, I must get the classical theory of nth order derivative. That must be the requirement. So when we define any fractional order derivative, we must that fractional order derivative must preserve this classical property. First property is the backward compatibility must have any fractional order derivative. Means if I am taking a real number by replaced by integer number, I must get the classical derivative. If I replace 0 in the order, I must get the function as it is. Okay. If I am defining any fractional order derivative and if I am denoting it by d raised to alpha, say, okay, it must satisfy this linearity property like d raised to alpha lambda ft plus mu of gt is equal to lambda d alpha ft plus mu d alpha of gt. Commutation property must be hold if I have the two real number alpha beta positive, okay, and it must give alpha order derivative of beta order derivative of f of t is equal to beta order derivative of alpha order derivative of f of t. It must preserve the semi-group property. Leibniz, the fractional derivative must be able to give the Leibniz formula, which is there for the classical nth order derivative, and we must able to give the formula for the chain rule. But unfortunately, all these properties are not preserved by the any of the derivative. That's why there are the number of definitions of the fractional order derivative, among which two derivatives are very popular. One is that Riemann-Liouville fractional derivative and another is the Caputo fractional derivative. Okay, so we will discuss the properties of these two fractional derivatives. We will start with the definition of Riemann-Liouville fractional integral. Okay, so we'll start with the classical integration. Suppose I am denoting this classical integration a to t f of s by the operator IA on the space of continuous function CAB. And if I will write this integral as I of f of t, okay, now if I am considering n-time integration, okay, so we know that Cauchy proved that n-time integration of the function can be represented in the form of single integral, 1 upon n minus 1 factorial a to t minus s n minus 1 f of s ts for t greater than 8. Okay, so as a mathematician, mathematicians are interested in generalization. So it has thought that can we replace the symbol n, natural number, by the positive real number? Okay, and it was because we have the generalization of factorial notation in the form of gamma. And what we must have after replacing alpha n by natural number n by the real order alpha, this integral must be exist. Okay, so and this work, if I am substituting n by the positive real number alpha and factorial notation n minus factorial by gamma of alpha, the Cauchy formula for the repeated integration is converted to the formula for the fractional integral equation, and it is given in the definition 1. If f is continuous function and alpha is real number which is greater than or equal to 0, okay. So alpha order integration of f of t is given by this 1 upon gamma alpha a to t minus s alpha minus 1 f of s ts when alpha is positive, and when alpha is equal to 0, we are defining it 0th order integration of f of t is equal to f of t, where gamma is your Euler gamma function. And we can see that if I am replacing this alpha by the natural number, I am getting the Cauchy formula for n time integration. And if we see the properties of fractional integral, Riemann-Liouville fractional integral, if you are considering f and g are the continuous function, and if I am taking the limit of fractional integration, alpha order integration of f of t as alpha tending to 0, it will give the function f of t. That's why it is reasonable to say 0th order integration of f of t is equal to f of t, as we have taken in this definition here. Okay, because of this theorem, we are able to write that. This fractional integral preserve the linearity property which are preserved for the your Riemann-Liouville integral, Riemann integration. Okay, commutation law is hold. Alpha order integration of beta order integration is same as beta order integration of alpha order integration. Semi-group properties also hold. Alpha order integration of beta order integration is same as alpha plus beta order integration of f of t. We can find out the integration of power function t minus a raised to mu, where mu is any real number greater than -1. This is natural, and we will get this formula of fractional integral of this function, power function. Okay, and we can say that this is the natural generalization of positive integer or positive integer properties. If I am taking a natural n order integration of t minus a raised to m, okay, and if we calculate this n time integration of this power function, I am getting this formula. If I am writing this in the using the definition of gamma function in this format, okay, I will get this. Okay, now if you are comparing these two formula, these two are coincides. If I am replacing alpha by n, mu by m, this formula get converted in this format. Constant integration I am getting in this format, okay, and integration of exponential function we are getting in the form of 2-parameter Mittag-Leffler function, which I will introduce later. Okay, we have found here only the integration of power function, constant, and exponential function. We have not given the integration of other functions because we know that many of the function, trigonometric function, okay, of which we can find out the ordinary integration can be represented in the form of power series or in the form of exponential function. Okay, knowing the fractional integral of exponential function and power function and constant, we can find out the fractional integration of other functions using these formulas. With having the knowledge of fractional integral in the sense of Riemann-Liouville fractional derivative, we will give the definition of fractional derivative in the sense of Riemann-Liouville. Okay, so we will suppose alpha greater than 0 is any real number. And we know that we can find out two consecutive numbers, say n minus 1 n, that sandwich your alpha. Having known with this property, alpha order derivative of f of t is defined in this sense. Classical nth order derivative of fractional n minus alpha integration of f of t when your alpha is between this. Okay. Now, if we consider integration as the inverse of derivative, okay, and if I am writing this classical derivative as d raised to n, and this I am writing as d raised to minus of n minus alpha, if I am considering integration as derivative, integration is inverse of derivative. D raised to n, d raised to minus of n minus alpha gives your d raised to alpha. This may be the way of defining Riemann-Liouville fractional derivative. Now, if I am taking alpha is equal to n here, n minus n gives your 0, and we have already seen that 0th order integration of f of t is what your f of t. So when alpha is equal to natural number, this derivative is converted to your classical derivative. Okay, so this is the beauty of this derivative. When I am putting your alpha by natural number, this is converted to your classical definition of derivative, nth order derivative. And when I am having alpha between n minus 1 to n, this is the derivative of alpha order derivative of f of t. This is the elaborated form of this definition. Now, when alpha is between n minus 1 to n, and if I am taking the limit of this derivative, when alpha is tending to n, okay, so left hand side limit as alpha tending to n of this derivative gives your classical nth order derivative, and when alpha is tending to n minus 1, it gives your n minus 1 the classical derivative of f. Okay, so we have already seen that when alpha is natural number, it converted to your classical derivative. Okay, so this theorem act as a bridge, gives the information about this Riemann-Liouville derivative. Okay, and it says that this Riemann-Liouville derivative operator act as a bridge between the two classical derivatives, n minus nth derivative and n minus 1 derivative. Means when I am putting alpha is equal to natural number, it converted to your classical n derivative. When I am putting your L is equal, alpha is equal to n minus 1, it converted to a classical n minus 1 derivative. And when alpha is between n minus 1, I have derivative in the sense of Riemann-Liouville. Okay, so this derivative act as a bridge between the two classical derivative. I know the classical derivative of n and n minus 1 order, and now I have the derivative of alpha order between n minus 1 and n. From above the theorem, it is reasonable to state that zeroth order derivative of f of t is the function itself. Okay, if I am taking a particular case n is equal to 1, this will be converted to 0 less than alpha less than 1. Okay, so this limit will be in this format, alpha tending to 0. Okay, and n is equal, if I am putting here n is equal to 1 here. Okay, so this limit is converted like this, alpha tending to 0, derivative of f of t of order alpha is 0th order classical derivative of f of t, and we know that 0th order classical derivative of f of t is f of t. Okay, so this theorem gives idea about why we are able to set 0th order derivative of function f of t is equal to f of t. We know that this classical nth order derivative we can write in the form of limit. Okay, and by method of substitution, s tending to 0 can be converted in the form of limit s tending to t. I am finding the derivative of nth order of the function f at the point t. So I can convert this limit in the form of s tending to t. And we know that to write the symbol of limit as s tending to t, t must be the limit point of the domain of function f. Okay, and from the definition of limit point, t has an arbitrary neighborhood. Okay, so nth order derivative, to define the classical nth order derivative of f of t, your function must be known in some arbitrary neighborhood using your definition of limit point. Okay, but when I am able to, when we are defining alpha order derivative of f of t, alpha order derivative of f of t, okay, we must know the function in this interval a to t. Okay, so that's why we are calling this classical derivative is the local operator, because we know the to define this classical nth order derivative of function f of t, our function must be known locally. Okay, and to define the concept of Riemann-Liouville fractional derivative, our function f of t must be known in the interval a to t. Okay, that's why we are calling fractional derivatives non-local derivative operator. Okay, again we have the formula for the power function of derivative. Okay, if you are considering the classical nth order derivative of the power function t minus a raised to m, okay, we are having the derivative in this format. Okay, and we can say that this formula is the natural generalization of your classical nth order derivative of power function t minus a raised to m. After replacing your alpha by n and mu by m, I am getting this formula. Okay, and when a Riemann-Liouville derivative of alpha order of t minus a raised to alpha minus m, when m is between 1, where m takes the value 1 to n minus 1, at that time this derivative is equal to 0. Derivative of constant is I am getting in this format. Okay, so this is the drawback of Riemann-Liouville derivative. Classical derivative gives constant derivative is equal to 0, but we are not getting the constant derivative in the form of 0. This is one of the drawback of the Riemann-Liouville derivative. Okay, that's why already I had told that whatever the number of definitions which I have shown you, that all definitions does not satisfy all the properties of classical order, classical derivative. Okay, therefore there are a lot of derivative, and this is due to the fact that different author, those who are defining the fractional derivative, they would like to preserve the properties of the classical derivatives. Again, I have the formula for this is fractional derivative of exponential function, which is given in the form of Mittag-Leffler function. And already I have told that if we know the derivative of power function, constant, and exponential function, other functions which are differentiable either can be expressed in the form of power series or can be expressed in the form of Mittag-Leffler function, in the form of exponential function. And using this formula, we can have the derivative of that function also. Now we'll see some properties of Riemann-Liouville derivative. Okay. When I am considering alpha and beta are positive, so we will discuss the case of alpha order derivative of integration of beta order of function f of t. Now, if we consider this alpha is greater than beta, this is converted to alpha minus beta order derivative. When alpha is equal to beta, derivative of integration of the function f of t gives f of t as it is when alpha is equal to beta. And when alpha is less than beta, okay, this is converted to your integration of order beta minus alpha. Okay. Now we will see the case of what will be the integration of derivative. So I am considering any order beta of integration, any order alpha of the derivative. And suppose alpha is sandwiched between the natural number n minus 1 to n. So integration of alpha to order derivative I am getting in this format. I am interesting when alpha and beta are same. So if I am taking in particular alpha is equal to beta, this formula is reduces in this format. Okay. Now compare this formula of integration of derivative with your classical case. Nth order integration of nth order derivative I am getting in this format. Okay, so I am getting the formula that resembles with your classical case, but just what happened, the classical derivative, the initial conditions which are generated in the form of classical derivative are not present here. So I am getting here conditions in the form of fractional derivative at t is equal to a. Okay, from this result and this result, when alpha is equal to beta, means derivative of alpha order of integration of alpha order of f of t is equal to f of t. So I can guess here from derivative of alpha order of integration of alpha order is equal to your identity function if I am considering as an operator. Okay, so I have this result. Alpha order derivative of alpha order integration is your identity operator, but from this alpha order integration of derivative is not equal to function f of t. This comes with your additional quantity. So these two, these are not equal. So your alpha order integration of d raised to alpha is not your identity operator. And this is the similar case as in your classical condition. That is nth order classical derivative of nth order integration gives your identity operator, but this is not the case here. Then I am taking reverse order, so I am getting this formula in that case. Now we'll see the composition. Okay, for the classical derivative, already I have explained that classical derivative satisfies your semigroup property as well as your commutative property. Means m and n are the natural number if I am taking. And if I am finding mth order derivative of nth order derivative, I am getting m plus nth order derivative that give the same result. And mth order derivative of nth order derivative is same as nth order derivative of mth order derivative. This is the this happen in the classical derivative case, but same is not happen for the Riemann-Liouville derivative. If I am considering m is natural number and alpha is real number, I am getting this mth order classical derivative of Riemann-Liouville derivative is Riemann-Liouville derivative of m plus alpha order. Okay, but I am if I am reversing this order, if I am taking first Riemann-Liouville derivative of classical derivative, this classical derivative I can call Riemann-Liouville derivative also, because I have already told that your Riemann-Liouville derivative, when I am taking a real number replaced by the classical natural number, it is converted to your classical mth order derivative. So alpha order derivative of mth order derivative, I am getting this result. Okay, and in general these two are not equal until and up to if this kth order derivative of f at a equal to 0. So we have the non-commutativity for Riemann-Liouville derivative like this. Okay, but to have all these three equality 1, 2, 3, all this must be equal. I must require this quantity equal to 0. And this quantity, this summation must be equal to 0 when kth order derivative of f at a equal to 0 for k equal to 0 to m minus 1. So I am getting your semi-group property and commutativity. I am taking what? Composition of m, the natural order derivative with real order derivative. Okay, so I am getting commutativity when our function satisfies this property. Okay. Now we have seen the composition of natural order with real order. Now we'll see with real order. Okay. So that must be your next result. Okay. But before that, I'll discuss this property using this formula. This result, mth order derivative of alpha order derivative can be written in Riemann-Liouville derivative of m plus alpha order. So this alpha order derivative using the property just shown to you can be written in this format. Okay. And this I can write in this way. So I am taking beta is equal to alpha minus n minus 1. Okay. And this alpha order derivative is written in the form of classical n minus 1th derivative of beta order Riemann-Liouville derivative. Okay. When beta is between what your 0 to 1. This automatically, when alpha is between n minus 1 to n, one can verify that this beta, when I am defining in this way, so beta will be get in the form of 0 to 1. We know the property of the classical derivative, so it is not therefore to study the behavior of alpha order derivative or alpha is any real number. It is sufficient to study that the behavior of derivative, Riemann-Liouville derivative, when beta is between 0 to 1. So if you see the literature related to fractional calculus and fractional differential equation, maximum theory has been developed with order beta between 0 to 1, means order between 0 to 1 because of this result only. Now we will see the composition of two Riemann-Liouville derivatives, real order derivatives. So I am taking alpha a real number, positive real number, beta positive real number. Let alpha is sandwiched between n minus 1 to n, and beta is sandwiched between m minus 1 to n. So I am having this result. Alpha order derivative of beta order derivative is equal to this. So I am not getting these two quantity are same. Alpha order derivative of beta, I am not getting alpha plus beta order derivative in the sense of Riemann-Liouville. This comes with some additional quantity. Okay. And having interchanged alpha and beta, I am getting this result. Okay. To have the semi-group and commutativity property simultaneously, we must have this summation is equal to 0. Okay. So we must have this condition, kth order derivative at a is equal to 0, where k is equal to 0 to r minus 1, where r is maximum of this m and n. And you will see that this is given in the form of fractional derivative, but I am writing this condition in the form of integer order classical derivative. And this is because of it is shown that in the book of Igor Podlimny that this condition is equivalent to what your class is, this condition. Okay. So I am getting commutativity as semi-group property if the function satisfies this condition. Kth order derivative at a is equal to 0 when k is from 0 to r minus 1. Okay. We have the Leibniz formula for the derivative. Okay. We know the classical formula, nth order derivative of f into g, that will goes from k equal to 0 to n, alpha choose k. Here is the classical derivative, f having order alpha minus n. Okay. But I am getting the Leibniz formula in the form of summation, where this summation is infinite because alpha choose k is does not vanishing when alpha is real number. Okay. This if I am taking the Laplace transform of your Riemann-Liouville derivative, I am getting this formula. Okay. This result. When I will compare this with classical derivative, natural order derivative, Laplace transform of this natural order derivative, I am getting this in this format, s raised to n f of s minus this. Okay. So we see that while solving the differential equation by using Laplace transform, our initial condition has been generated in the form of classical derivative, but this is not the case in the sense of Riemann-Liouville. Okay, so this is one of the drawback again for the Riemann-Liouville derivative, because to model any type of problem in the form of fractional differential equation, our initial condition must be in the form of your classical derivative, because we can give the meaning to the classical derivative. Suppose if I am taking s is the displacement at time t, If I am taking t is equal to 0, so I am getting initial displacement. If I am taking velocity, means derivative of displacement, okay, that is your x dash of t. Okay, if I am taking t is equal to 0, x dash at 0 gives what? Velocity at initial time. Similar that's why this is the drawback, because I am not able to. We are there is a no classical. There is a no physical meaning for the fractional derivative. Okay, so this is one of the drawback. Okay, so I have listed here some of the limitation of RL fractional derivative. Okay, so if we see the literature, maximum theory of fractional differential equation has been developed with Riemann-Liouville fractional derivative. Okay, so although Riemann-Liouville fractional derivative is well defined, it has some problem when it comes to apply to the physical problem. It does not use constant derivative is equal to 0. This might be an issue when using RL derivative operator for writing the differential equation. If I am taking limit of this derivative as t tending to 0, it gives infinity unless your kth order derivative of f at a is equal to 0. This might be an issue when applying to the boundary condition. And just I have seen that Laplace transform of RL fractional derivative depends on the fractional derivative at 0. This might be an issue while solving the initial value problem. Okay, that's why there is another definition has been introduced by the mathematician Caputo. Okay, in 1967, just to have reversed the order of Riemann-Liouville derivative. So we have seen that Riemann-Liouville derivative is what? Classical nth order derivative of n minus alpha order fractional integral. So Caputo, we can find the reverse order, n minus alpha order integration of classical nth order derivative. Okay, again, if I am taking alpha is equal to n here, so n minus n I am getting here 0. So 0th order integration of again gives this function as it is. So when alpha is equal to n, this Caputo derivatives gives your classical derivative as it is. Okay, and when alpha is between n minus 1 to n, this is the elaborated form of this. Okay, if I am taking limiting case when alpha tending to n, I am getting classical nth order derivative, but when I am taking alpha tending to n minus 1, I am not getting this classical n minus 1 derivative. This will come with the additional quantity minus of fractional order n minus 1 derivative at a. Okay, so fractional Caputo fractional derivative has upper consistency, means this alpha tending to n, it gives your classical derivative, but I have no lower order consistency. Now, if I am considering alpha between two natural number, consecutive natural number n minus 1 to n, okay, and if I am finding alpha order integration of Caputo derivative, I am getting this formula. And if I am comparing with your classical case, integration of nth order derivative of f of t, I am getting this formula. Okay, so you will say that you will see that integration of derivative appears in the form of classical derivative. Okay, and this is important while converting your fractional derivative in the form of integral equation. Okay, and this result again gives the information that when I am considering differential equation in the form of integral equation, the initial conditions are generated in the form of classical derivative, to which I can give the physical meaning. So that's why Caputo derivative is important in the UAP application point of view. And if I am comparing these two results, if I am replacing this alpha by the natural number, these two formula, I am getting, if I am replacing alpha is by natural number, I am getting this formula of the classical case. Again, I can find out, we can note that constant derivative I am getting here 0, which is not case in the real Riemann-Liouville derivative. I have the formula for the derivative of power functions, which again resembles with your classical case. And I can have the formula. I have the formula for the derivative of exponential function in the form of Mittag-Leffler function. Again, as I have already discussed that, I can find out the derivative of other functions in the sense of Caputo using these three results. Again, there is a problem with the commutativity. Similar to the Riemann-Liouville derivative, Caputo also does not satisfy the semigroup property in general as well as commutative property in general. It satisfies with certain restriction, means your kth order derivative at a must be 0. Then I have the Caputo alpha order derivative of Caputo mth order derivative. I am calling this Caputo because when I have considered Caputo, order natural, it gives your classical derivative. So I am getting this property. This is your semi-group property, and this is your commutativity property. But in the particular case, when your function f satisfies this condition, kth order of derivative at a is equal to 0 for when k is equal to n plus 1, k is equal to n plus 1 up to m. Okay. Again, using this property, alpha order derivative of mth order derivative is same as alpha plus mth order derivative in the sense of Caputo. I can write alpha order derivative of Caputo in this format. Okay. So again, I am taking this quantity is beta, which is between 0 to 1. Okay. So already I have discussed that we know the property of classical n minus 1th order derivative. Okay. So to study the behavior of any order alpha in the sense of Caputo, we need to study the derivative. We need to study the behavior of Caputo derivative of order beta between 0 to 1. Okay. We'll see the relation between Riemann-Liouville Caputo derivative. So this is your definition of Riemann-Liouville derivative, and this is definition of Caputo derivative. Even if you are considering the classical case, we don't have this property. Derivative of integration is not equal to integration of derivative. Same is for your fractional case also. Derivative of integration is not equal to integration of derivative. Okay. So as these two are not equal, I can't expect that Riemann-Liouville derivative is same as your classical derivative. Okay. This is the result which gives a relation between your Caputo derivative and Riemann-Liouville derivative. So if I'm alpha is between n minus 1 to n, and if you assume that both derivative are exist for this function f of t, then Caputo derivative can be expressed in this format. We can observe that this is your n terms of Taylor series expansion of the function f. This is your n terms of Taylor series expansion of f about a. Okay. So to have these two derivatives same, in generally these two derivatives are not same. To have these two derivatives same, we must have this term must be 0, and this happen only if kth order derivative of f at a equal to 0. Okay, so Riemann-Liouville derivative and Caputo derivative same in this particular case. We can obtain the Leibniz formula for the Caputo derivative using the relation between Riemann-Liouville derivative and Caputo derivative. This is again important property to be noted. If I am finding the Laplace transform of Caputo derivative, I am getting in this format. Okay, so one of the property which we have to note here, I am getting Laplace transform in the form of classical derivative, and that will be very helpful while considering the differential equation in the form of Caputo, in which the initial conditions are generated in the form of classical derivative, to which we have the physical meaning. Again, we know the Laplace transform of nth order classical derivative, which is in this format. Okay. One can note that if I am taking this alpha is natural number, this derivative is converted to your classical derivative, and I am getting from this result, I am getting this result of the classical case. Okay, so I am getting the same result in the Caputo case as in your classical case. The important aspect of Caputo derivative is that it gives constant derivative is equal to 0. Limit of Caputo derivative as t tending to a, it gives 0, and this will useful while considering the boundary value problem. And Laplace transform of Caputo fractional derivative is the generalization of Laplace transform of integer order derivative, which I have already explained. Okay, and this is not the case in the sense of Riemann-Liouville derivative. Okay. Now we will compare the Riemann-Liouville and Caputo. So we have seen that Laplace transform of Riemann-Liouville derivative involves the initial condition in the form of fractional derivative and integral. But in Caputo case, we have the initial condition in the form of integer order. Okay. Laplace transform of Caputo fractional derivative is a generalization of Laplace transform of integer order derivative. When I am taking alpha is natural number, I am getting the formula for Laplace transform of nth order derivative, and this is not the case in the sense of Riemann. Okay, but definition of Caputo is more restrictive than your Riemann-Liouville, because to define the Riemann-Liouville derivative, continuity of the function is sufficient, but to define the Caputo derivative of f of t, I require the integrability of nth order derivative. In Riemann-Liouville, I just require the integrability of f. Okay, so Riemann-Liouville derivative exists for the larger class than the your Caputo case. Why these two derivatives are most used in literature? Because Riemann-Liouville derivative plays important role mainly in the development of the theory of fractional derivative and integral, and for application in pure mathematics. While Caputo derivative is suitable for applying in modeling. Applied problem require proper definition of fractional derivative, which can provide initial condition with clear physical interpretation, and that has been given by that appears in the form of Caputo. Okay, so this makes Caputo derivative more suitable to applied problems. Okay, so again, I will. Can I continue up to 5 minutes again? Any problem?
Sir, you can continue for 5 minutes.
No, sir.
Yes, sir.
Okay, right. Okay. So this is the existence theorem. As there are many PG students which have studied the book of E.A. Coddington, and you have studied existence and uniqueness theory for y dash is equal to f dy. So I am considering this problem in the sense of Caputo. Okay, and we have this result, existence theorem, as in the case of your ordinary differential equation. Okay, so alpha is between say 0 to 1. Okay. Y0 is some real number, k is some positive real number, beta is greater than 0, and I am considering this rectangle 0 to b cross this interval. Okay, and if I am considering this function f from g to r is continuous. Okay, and we know that any continuous function on compact interval, this is the rectangle. Okay, this we can in the language of metric space we can call this is your 2 cell, and every k cell, n cell we will call it is compact. And any continuous function on complex, it is bounded. Therefore, the boundaries exist for this function on this rectangle. I will take that bound is m. Okay. And if I am defining t is equal to b, means this, if m is equal to 0, and if I am defining t is equal to minimum of b and this quantity, otherwise, means when m is not equal to 0, then there exists a solution in the space 0 to t, space of continuous function, solving the initial value problem. This is your non-linear initial value problem, and this is your existence theorem. Means under this condition, under the continuity of f on rectangle, I have the solution in this space 0 to t when I am defining t in this fashion. Okay. If I am considering the particular case, okay, under the same assumption, okay, this initial value problem, this initial value problem can be written in the form of equivalent integral equation, as in the case of your classical differential equation, nonlinear classical differential equation of first order. As you know, when I am taking alpha tending to 1, okay, alpha tending to 1, this will be converted to your classical derivative, as already we have discussed. So this problem will be converted to what your y dash of t is equal to f t y t, y at 0 is equal to y naught. And as a particular case of this result, I am getting the theorem for the classical case. If y is in the space of continuous function from 0 to b, on 0 to b, then this differential equation, nonlinear differential equation, is equivalent to your this integral equation. This result we have proved in the book of E.A. Coddington, those in your PG classes. Okay. I will discuss the non-local nature of fractional derivative through this fractional integral. I am considering this fractional integral. Okay. And I will consider classical case as well as your derivative case, fractional derivative case. Okay. So if I am taking alpha is between 0 to 1 and t1, t2 in this interval, having this property t1 and t2. And if I am calculating difference yt2 minus yt1 from the equivalent integral equation of fractional differential equation 1, I am getting in this format. Okay, so 0 to t2 I can write in the form of 0 to t1 and t1 to t2. So I am getting this integral here t1 to t2, and this integral from 0 to t1 and combined with this is converted in this format. Okay. Now, as already I have discussed, if I am taking alpha is equal to 1, this get vanished. This term get converted to 1, and yt2 minus yt1 is converted in this format. Okay. Now, if we know y at t1 and I have to calculate y at t2 for any t2 greater than t1, I need the information only at this point and the function f. Okay. So if we already know the solution yt1 of our initial value problem at point t1, then we may compute the solution at point t2, which is greater than t1, any point, explicitly on the basis of yt1 and f, and we do not need the use of any information of this y on this interval 0 to t1. Okay, so having just only known your function at point t1, I can calculate your value of yt2. Okay, therefore, this equation states that it is sufficient to observe that the state of first order system at an arbitrary point in time to compute its behavior in the future. Okay, so to compute state in the future, we just need the information of the function at a single arbitrary point. Okay, but this is not the case in the real order derivative. Okay, alpha order derivative between 0 to 1. Okay, when alpha is between 0 to 1, our expression, which I have written it again here. Okay, and when alpha is between 0 to 1, this doesn't vanish in any case. Okay, therefore, if I would like to calculate the value at certain point, say yt2, I must know this function y from 0 to t1 and t1 to t2. So we have this observation: the first integral on the right hand side of 6 does not vanish in general. Hence, whenever we want to compute the solution yt2 at some point t2, it is necessary to take into account the entire history of this function y from 0 to t1 and t1 to t2 means 0 to t2 we required. Therefore, this reflects the non-locality of the Caputo fractional derivative operator, this nature. Okay. Therefore, fractional order differential equations are more important when we are considering the physical phenomena which has memory effect. Okay, so any physical phenomena which has memory effect can be suitably modeled with the fractional order derivative. Okay, so again, this is your Mittag-Leffler function. Okay, which is the E alpha first order one parameter order Mittag-Leffler function. E alpha of z is equal to, in this form summation we will define when z is equal, z belongs to C. This is introduced by Mittag-Leffler. This is two parameter Mittag-Leffler function. Alpha and beta are positive. Okay, when I am taking alpha is equal to 1, beta is equal to 1, your first order one parameter Mittag-Leffler function is converted into form of your exponential function. When I am taking alpha is equal to beta is equal to 1, this two parameter Mittag-Leffler function converted in the form of your exponential function. So from this observation, we can say that Mittag-Leffler function of one parameter or two parameter is generalization of your exponential function. Okay. Now, friends, we have seen in the theory of ordinary differential equation, exponential function plays very important role while finding the solution of linear integer order derivative constant coefficient. What we are doing at that time, we are converting linear order ordinary differential equation in the form of characteristic polynomial. We are finding the root for the characteristic polynomial. Using that root, we are writing the solution in the form of exponential function. The role which are played by the exponential function in linear order differential equation, similar type of role is also played by Mittag-Leffler function in linear fractional ordinary differential equations. So that I will discuss next. So these are some cases, particular cases. So I can generate cos hyperbolic function, sine hyperbolic function, sine cos from Mittag-Leffler function, and other function, remaining other trigonometric function I can generate from this sine cos and sine hyperbolic cos hyperbolic, an exponential function. Okay, so an application of Laplace transform for this initial value problem, which is linear non-homogeneous fractional ordinary differential equation involving Caputo derivative. If I am solving equation 7, initial value problem 7 using your Laplace transform, I am getting this formula, equivalent integral equation, which is in the form of Mittag-Leffler function. Okay. So if I am taking the limiting case alpha tending to 1, it will be converted. If I am considering the particular case when alpha is between 0 to 1, okay, so n is equal to 1. If I am taking here n is equal to 1, so it will be converted to 0 less than alpha less than or equal to 1. So that theorem is reduces in this format. Okay, an integral equation is reduces in this format. But if I am considering the limiting case alpha tending to 1, so this Caputo derivative is converted in the form of your classical derivative y dash. Okay. And this Mittag-Leffler function I am converted to what your exponential function. So this result is converted in this format, and which we have solved this in ordinary differential equation. Okay, so see your first order differential equation, linear differential equation, we can give the solution in the form of exponential function, while linear differential equation in the form of Caputo, we can give the solution in the form of what your Mittag-Leffler function. Okay. So with this basic, I will stop here. These are the books which I have referred to prepare this presentation. Okay. So this is not the research material which I have already presented to you. Okay. So these are the material which I have taken mainly from the book of Caputo. Kai Dithel. Okay. Igor Podlimny, Kai Dithel, and Kilbas Srivastava I have used, and these are the other references which we have used. Okay. Thank you. And next is open for discussion.
Thank you, sir. There are a few questions. So should I ask, sir?
Yes, please, sir. Please.
So first question is why fractional derivative and integration?
Okay, sir. Already have explained this thing. Mathematicians are interested in generalization. Okay. Classical derivatives are defined for the natural numbers: first order derivative, second order derivative, third order derivative, fourth order derivative. Okay, so mathematicians are interested to fill the gap between classical order two derivatives. Suppose first order derivative and second order derivative. Can we think derivative of half order? Can we think the derivative of 1.5 order? Okay. Can we think the derivative of pi order? Even can I think the derivative of complex order? To answer this question, mathematicians has thought to generalize the concept of classical derivative. That's why the derivative of fractional order, derivative has been arised. And one of the most important aspect of the fractional derivative is that, okay, many physical phenomena which we are considering with the classical derivative, okay, that cannot be modeled for the phenomena which have the memory effect, okay, means in which the history of the state is required, that cannot be modeled suitably with the classical derivative. Okay, with the non-local nature of the fractional derivative, the physical phenomena in which the state is dependent upon its history are more suitable to model using your fractional order derivative. I think I have tried in better way to give the answer of this question.
Yes, sir. Sir, another question is that apart from the constant function property, which is other differences between RL and Caputo fractional derivatives, yes, one can tell to students in simpler manner.
The actually two derivatives are different because Riemann-Liouville derivative is defined in the sense of classical derivative of fractional integral, and Caputo derivative is defined in the form of fractional integral of classical derivative. Okay, and I have already discussed that in general derivative of integration is not equal to integration of derivatives. So these two derivatives are not coincides in generally until and up to it satisfies certain condition. Okay, this is one thing. Second thing, I have discussed in the sense of Laplace transform. Okay, if I am taking the derivative of Laplace transform of Caputo derivative, we are getting the same type of effect as in the case of classical. Okay, so the conditions, initial conditions are generated in the form of classical derivative to which I can give the physical meaning. But this is not the case in the Riemann-Liouville derivative. The Laplace transform generate initial condition in the form of fractional derivative, and till now there is no geometrical as well as physical meaning have been provided by any mathematician in the perfect form. Many mathematicians are trying to give the geometrical as well as physical meaning, but till today there is no perfect meaning has been given geometrically as well as physically for fractional derivatives.
Thank you, sir. Sir, there are many questions, but this would be last question. What are research scope in fractional derivative by numerical methods? What are research scope?
Sir, whatever the thing easily happen in the classical order derivative, same type of thing we can't expect in the fractional derivative, sir.
So is there any scope?
Yes. many numerical method has been developed for study of fractional differential equation in the sense of numerical way. One of the researcher, Maharashtrian researcher from Pune, Professor Varsha Gidje madam, and second speaker of this national conference, Professor Bhalekar sir, they have developed numerical methods for fractional differential equation. To deal fractional differential equation numerically and by way of approximation method. Okay, so for this question, Bhalekar sir is more suitable to give the proper answer.
Yes.
I think.
And some participants ask to share textbooks which you have told in this lecture. So maybe in your chat box you have some chats or messages. So maybe you can reply, sir.
Yes. So I will suggest for the beginner, you can refer this fourth number reference, Igor Podlomini, and this book by Kai Dithel. Okay, this for the beginners, you can grasp the things very easily. Okay, other books are very important, also very important, but for the beginner, I will suggest this reference number 4 and 6.
Okay, sir. Okay, sir. Thank you, sir.
Thank you very much, sir. Thank you very much for giving me an opportunity to talk in this national webinar. Thank you to organizing committee. Thank you very much, sir.
Now I request Mr. Ramesh Shinde to propose the vote of thanks for this session.
I'm thankful of our speaker. Thank you, sir.
Thank you very much, sir.
Has given nice lecture on fractional basics in fractional calculus. Basically, sir has covered history, developments, and most various types of fractional derivatives. Thank you, sir. Thank you from all participants which are present right now, present in our Zoom, and also from behalf of all our YouTube viewers. Thank you. Thank you very much, sir.
Thank you, sir. Thank you very much.
Thank you, Shinde, sir. Now I request Dr. Jayant Patade, Assistant Professor, Department of Mathematics, Jaysingpur College, Jaysingpur, to introduce our next speaker, Dr. Sachin Kumar Bhalekar, sir. Patade, sir? Dr. Patade, are you there?
Yes, sir.
Yes, you can start.
Good afternoon to all of you. Today is my great pleasure to introduce the second speaker and my beloved guide, Dr. Sachin Kumar Bhalekar, Associate Professor, School of Mathematics and Statistics, University of Hyderabad. Sir has completed his BSc with distinction from New Arts, Commerce and Science College, Ahmednagar in 2005 and master degree with distinction from the University of Pune in 2007. He qualified SET NET GRF in 2008 and GATE in 2010 with All India rank 155. He completed his PhD degree in 2011 from the Pune University and honored Padma Shri late N.S. Venkatesan Gold Medal for his best PhD thesis entitled Investigations in Nonlinear Systems of Fractional Order in Mathematics from the University of Pune. He has worked as an assistant professor in Department of Mathematics, Shivaji University, Kolhapur from 2011 to March 2020 and recently working as an associate professor in School of Mathematics and Statistics, University of Hyderabad. His more than 50 research articles published in reputed international journals are indexed in SCI, Web of Science, Scopus, etc. Also, 9 book chapters are published in national and international edited books. Sir has edited one international book entitled Frontiers in Fractional Calculus. The research article entitled Chaos in the Fractional Order Nonlinear Block Equation with Delay and 6 such research article has been in top 25 hottest articles in respective journals of Science Direct. His article, Boundary Value Problem for Multi-Term Fractional Differential Equations, is in the top 10 research paper of India in 2009. In 2018, he has honored A.M. Mathai Research Excellence Award from Society for Special Function and Their Applications for his excellent research. He has 2,366 Google Scholar citation with H-index 24 and item index 38. Also, 1,225 Scopus citations with 19 H-index. Sir has presented his research work at national and international conferences. Also, he has given invited talks in many workshops, seminars, and conferences. Sir has research collaboration with various international universities. He worked on the 3 major and 1 minor research project and guided 2 PhD students and 1 his student awarded PhD degree. Today we have such a well-known personality in mathematics with us, Dr. Sachin Kumar Bhalekar. Now I request to Bhalekar sir to start the invited speech on topic chaos in dynamical system. Please sir, carry on sir.
Thank you everyone. Am I audible, Javan?
Yes, sir.
Okay, fine. Hello everyone. In the today's lecture, we discuss some basics about the course on dynamical systems, especially chaos in dynamical systems. So it is a very famous branch of mathematics, and this branch deals with qualitative and quantitative analysis of various equations. Here, qualitative analysis means study some properties like stability of solution, boundedness, etc. And quantitative analysis means actual finding solution. So the definition of dynamical system is given as it is evolution rule, and it defines a solution trajectory which is function of single parameter. Say usually the parameter is time t, and it is on the set of state variables. Actually, dynamical systems are not different. We study dynamical systems from our 12th standard or 11th standard. These are nothing but differential equations where the time is continuous. So the differential equations are called as continuous dynamical systems. There are discrete dynamical systems also where time is not continuous. These are called as maps, or we can say sequences. So everyone has studied sequences. So the sequences are nothing but discrete dynamical systems. There are few more involved systems also, but basically we deal with these two examples.
Hello sir, excuse me sir.
Yes.
Please
Sorry.
Zoom your screen, sir. Zoom your screen, sir.
Okay. Fine.
Okay.
So before going to non-linear systems, I will explain some linear analysis.
Full screen, sir. Please.
Yeah, actually, I want to share another screen.
Okay.
Okay. So simple case we study is dx by dt equal to capital AX. We call dx by dt to be x dot, which is differentiation with respect to time, and capital A here is n by n real matrix. And of course, capital X is function of t, and its values are in Rn, real values. So we can say that it is system of differential equations or simultaneous equation. Simple equation with n equal to 2 is capital X is small x, small y. So that capital X dot, we can write derivative of x, x dot, and y dot. So this is column vector equal to matrix A. We can take any matrix A, 1, minus 4, 3, 2 into capital X means xy. So if we expand this, then it is nothing but x dot equal to x minus 4y and y dot equal to 3x plus 2y. So such systems are there at graduation level. Okay, but here we discuss qualitative analysis also. So when we consider matrix, then important thing is eigenvalue of matrix. Okay, so our first important result is if lambda is eigenvalue of matrix A and capital V is corresponding eigenvector, then the function e raised to lambda t into V is solution of differential equation x dot equal to ax. Okay, so we are using eigenvalues and eigenvectors of matrix A to obtain solution of this system. It is not difficult to check. So if we write x for e raised to lambda t into V, then its derivative dx by dt or x dot is derivative of right hand side with respect to t. V vector V is constant vector. Differentiation of e raised to lambda t is lambda e raised to lambda t. V is column vector. Lambda and e raised to lambda t are real numbers. So we can write this as e raised to lambda t multiplied by lambda v, because e raised to lambda t and lambda both are real numbers. Commutativity is there. And now we consider this second term lambda multiplied by v. We know that lambda is eigenvalue and v is eigenvectors for matrix A. So A multiplied by v must be equal to lambda into v. So this is nothing but e raised to lambda t into a v. Again, this e raised to lambda t is a real number, so it can be anywhere. So we rewrite this equation as a multiplied by e raised to lambda t into v, no harm. A is n by n matrix, V is column vector in Rn, e raised to lambda t is a number. Now what is e raised to lambda t into v? E raised to lambda t into v is capital X. So this is right hand side is nothing but ax. So what we get when we have taken differentiation of x dot, then we found that x dot is nothing but x. In other words, the function x defined by e raised to lambda t into v satisfies equation 1. means this is solution of differential equation x dot equal to capital A into x. Okay. So this is the role of eigenvalues and eigenvectors in finding solution of this system. Okay. Now this is particular solution of this system. Important question is, what is general solution? How to find general solution? So there are different ways to find general solution. So I will quickly go through the method to find general solution. I will not give proofs. Proofs are given in a famous book, which I will suggest. Book is Differential Equations, Dynamical Systems, and Introduction to Chaos. It is by Hirsch, Smell, and Devane. So all these things will be there. So let us see what will be the general solution. There are different cases, of course, depending on eigenvalues. So if this n by n matrix A has eigenvalues lambda 1, lambda 2, and so on, lambda n, and corresponding eigenvectors v1, v2, and so on, vn, and these are n number of independent eigenvectors. Okay, so note that eigenvalues may be repeated, but we must have n number of eigenvectors. N is order of this matrix. So A is n by n matrix. So here these independent eigenvectors, then summation Ci e raised to lambda I t vi I equal to 1 to n. Okay, where C1, C2, and so on, Cn, these are arbitrary constants involved in this nth order system. So this is general solution of, then this is general solution of x dot equal to Ax, this system. Okay. Of course, we can have repeated eigenvalues. In that case, we will not have, in some cases, when we have repeated eigenvalues, we will not have n number of independent eigenvectors. So in that case, we have to find generalized eigenvectors. Okay, so this part is related with linear algebra. So we have to find canonical forms, and then easily we can find general solution. Okay, so actually, what is the relation between canonical form and the original system? Okay, so let me explain. So another important result is relation between the standard system with standard canonical form as a coefficient matrix and the given system. Okay, so suppose T is invertible n by n matrix such that B equal to T inverse AT is canonical form, then standard canonical form has a coefficient matrix, and then what we have to do? We define y to be t multiplied by x. Okay, Therefore, what is derivative of y? Y dot? It is t is constant matrix differentiation of x. And what is differentiation of x? It is x. So right hand side is t ax. Okay. Now we multiply. We write here x as, okay, if y is tx, then x must be t inverse y because t is invertible. So we multiply this equation from left by t inverse so that we get t inverse y is x. And here we write t a multiplied by t inverse y. Now t inverse is equal to b, and here we get equation as y dot equal to by. So original system was x dot equal to ax, new system is y dot equal to by. What is benefit of this system? The matrix A can have any form, but B is canonical form. Okay, and handling canonical form is always simpler. We can always define general solution using canonical forms. Okay, so we have some examples here, and let me discuss about the stability result. So stability properties of this system depend on eigenvalues. So result is, if real part of lambda is negative for all eigenvalues lambda of A, then all solutions of given system x dot equal to ax tend to origin as t tends to infinity. Okay, so this is qualitative property. We are saying that solutions are tending to origin as t tends to infinity. It is because our solution contains e raised to lambda t into v, and if eigenvalue is real part is negative, means lambda is negative number, and e raised to negative number multiplied by t, its limit must be 0. So all the components tend to 0. That means solution is tending to origin. Of course, we can have complex eigenvalue case. If we have complex eigenvalues, then complex eigenvalue takes the form u plus minus iv. Okay, where I is complex number. In this case, e raised to lambda t, let us take plus value only. So e raised to lambda t is e raised to u t plus iv t. So that is e raised to ut multiplied by e raised to iv t, and this is e raised to ut into e raised to iv t is cos vt plus I times sin vt. Now note that the term cos vt plus I sin vt, for any t, it will be on the unit circle, so it cannot become unbounded. So the condition for stability is this first part, that is e raised to ut. This must be bounded. So result is e raised to lambda t will be bounded if e raised to ut is bounded. And what is u here? U is nothing but real part of lambda. Okay, So u is real part of lambda, and we know that if u is negative, then this will tend to 0. So the general result is, if real part of eigenvalue is negative, then solutions tend to origin. Okay, so I want to share some demonstrations using one software. So let me share another screen. This is software WinPlot, which is freely available to download, and we can easily compute various dynamical systems using this software. So when you open this, you will find in menu bar Windows. In Windows, there is 2dim. So open that 2dim, then check. There are again menus. So go to equation menu and then go to differential. Then we are going to consider two-dimensional systems. So the second option is for two-dimensional system, dx by dt. Okay. So here we consider first example as x dot equal to 6x minus 5y. Okay, linear equation. 6x minus 5y, and second equation is y dash is minus 5x plus 6y, and then we there are options. So field, we consider vector field. So vector field is also important part in studying dynamical system. So you can find that there are some directions for solutions. So let us see actual solutions. So in menu bar, consider one menu one, then go to initial value problems and give some initial value of your choice. T is 0, what is x and what is y? So initially it is 0, no any issue. Then there are different options: forward orbit, reverse orbit, and both orbits. So we consider forward orbit means what happens as we increase value of time t and draw. Okay. So when solution is at origin, it will stay always there. Now click anywhere. So you will find solution starting at that point. So we can say that in this part solution is going away. Now if we click here, it is also going away. So almost all solutions are tending away from origin. So such case is called as unstable system or source. So all the solutions starting in the neighborhood of origin, they are going away from origin. Okay, so this is quantitative analysis. We have solved this system and found out the solution. Now, what is relation with eigenvalues and eigenvector? So again, let me share another screen. Okay, so here I will explain the relation with eigenvalues. So we consider x dot equal to, our coefficient matrix is 6 minus 5 minus 5 6 into x. Okay, so x is small x and small y. So our system was x dot equal to 6x minus 5y, and second equation was y dot equal to minus 5x plus 6y. Okay, and we have verified that all the solutions starting in the neighborhood of origin tend away from origin. So here we find eigenvalues of this matrix. Okay, so if we write this as AX, then eigenvalues of matrix A are 6 minus 5 and 6 plus 5. Okay, so eigenvalues are lambda 1 equal to 1, lambda 2 equal to 11. Both the eigenvalues are positive, and we know that solution contains the term e raised to lambda t. Okay, so both the eigenvalues are positive. So e raised to lambda t as t tends to infinity must tend away from origin. Okay, so all the solutions are unbounded except the solution which starts at origin. Okay, so this is qualitative analysis. Of course, there is a role of eigenvectors. Here, eigenvectors are, first eigenvector is 1, 1. So this represents the line y equal to x, and second eigenvector is 1 minus 1. So this is related with the equation x equal to minus y or y equal to minus x. So let us see the role of eigenvector also. I am sharing again the screen of the software. Okay, so you can clearly see that the line y equal to x is straight line. So vector, eigenvector. Okay, so the solution star whose the solution of this system of differential equation whose initial condition is that eigenvector will always add the eigenvector. Okay, so these are straight line solutions. Another eigenvector is y equal to minus x. You can see that it is also straight line. So other things are other things also seem straight line, but they are not actually straight lines. So in the neighborhood of origin, there are curved things. Okay. So similar things can be with negative eigenvalues. Then in that case, we call it as sink. If one eigenvalue is positive, other is negative, it is called as saddle, because some solutions are stable, others are unstable, and we can have complex eigenvalues. Okay, so I will suggest to refer that book by Hirsch. Now let us move to non-linear systems. Okay. So when we consider non-linear system, this is general form x dot equal to f of x. In previous case, we studied x dot equal to capital A multiplied by x, capital A was matrix. Now here f is a non-linear function. We take this function to be continuously differentiable function because we want a unique solution to initial value problem formed using this equation. Okay. So in linear case, we have seen that the origin was important, means the solution starting at origin was always at origin. Similarly, in case of nonlinear equation x dot equal to f of x, the constant solutions or steady state solutions are called equilibrium points or equilibrium solutions. Okay, so if we put x equal to constant equal to x star, then its derivative will be 0. So all components of this vector are 0, and right hand side is f of x star. So how to find equilibrium? We have to solve the equation f of x star equal to 0. 0 means here origin in R. Now this equilibrium is called stable if nearby starting solutions stay nearby. Means we consider x star, then there is a neighborhood of x star such that if we take initial condition in this neighborhood, then the resulting solution of this system stay nearby. Means it will not be unbounded. Okay. This equilibrium is asymptotically stable if it is stable and nearby starting solutions converge to X star. Okay. In the first case, we just say the nearby starting solutions stay nearby. In the second case, we are saying that these are converging to X star. So it is the case of asymptotically stable. And third case is unstable. Unstable means which is not stable. Okay. Now analyzing nonlinear system. We know that nonlinear systems are not easy to handle. Okay. So finding solution of linear system is easy task. We can always find eigenvalues, eigenvectors. Even we can have generalized eigenvectors, and we always have exact solution. But it is not the case with nonlinear system. In general, we cannot have exact solution to nonlinear system. Of course, we can solve numerically. Okay, so under these conditions, we can have numerical solution. But for numerical solution, we have to specify all the parameters as well as initial conditions. For qualitative analysis, we don't need this. Okay, and we are going to relate this system with linear system. Okay, so what we do, we consider a solution which is in the neighborhood of X star. Okay, so capital X is solution of given system X dot equal to f of X in the neighborhood of X star. And now we define capital Y to be X minus X star. So this is error. Okay, or difference between equilibrium solution and the solution which is in the neighborhood. Now let us find derivative of this y. So y dot is d by dt of right hand side. Right hand side is x minus x star. So it is x dot minus derivative of x star. But x star is constant solution, steady state solution. So its differentiation is zero vector. So it is simply x dot. But what is x dot? X dot is f of x, our given equation. Now we replace x by y plus x star because y is x minus x star. So our equation is f of x star plus x. Now our function f is continuously differentiable. So we can approximate using first order Taylor's formula. So this is f of x star plus derivative of f at x star into y. Remember that this df of x star derivative is Jacobian matrix. It exists because function is continuously differentiable, and it is n by n matrix. Now what is f of x star? F of x star is zero vector because x star is equilibrium, and we get y dot equal to capital AY. Capital A is n by n matrix, which is Jacobian of function f evaluated at x star. Okay, so locally the nonlinear equation 1 x dot equal to f of x is equivalent to linearized equation y dot equal to A by this matrix A, which is Jacobian, is very important in this analysis. So here we don't want a zero eigenvalue or eigenvalue with zero real part. In that case, the analysis is quite difficult. Okay, so we say that equilibrium is hyperbolic if no eigenvalue of this Jacobian has its real part equal to zero. Okay. Now the definition. So stability analysis. So equilibrium point x star is called sink. Sink means all the nearby starting solutions tend to x star. So if all the eigenvalues of Jacobian matrix have negative real part. Okay. So recall the linear analysis. What we said? We said that if eigenvalues of coefficient matrix of linear system have negative real part, then all the solutions tend to origin of equilibrium of linear system. Here we say that if all the eigenvalues of Jacobian matrix at x star have negative real parts, then all the nearby. Okay, here we should say nearby because the linearization of nonlinear system is local. Okay, in small neighborhood. So we all these solutions tend to equilibrium. On the other hand, The equilibrium is called source or unstable if all the eigenvalues of Jacobian have positive real parts. Okay, it may happen that some eigenvalues are with positive real part and some with negative real part. In that case, we say that equilibrium is sad. Of course, we can have imaginary eigenvalues. So, if eigenvalues are purely imaginary, it is center. It is called as center. Now, there is important result in dynamical systems. It is called as Hartmann-Grobman theorem. It says roughly, it says that the behavior of a dynamical system, nonlinear dynamical system, one in a domain near hyperbolic equilibrium point is qualitatively the same as the behavior of its linearization. Okay, so these things are proved. So qualitative analysis of nonlinear system is locally same as its linearization. Okay, so proof of this result is given in the books on dynamical systems. In the last, I will share some references. Okay, so what this means, sink is asymptotically stable and sources are unstable, saddles are also unstable. So I don't have sufficient time, so I'm just showing solved examples. Otherwise, it is possible to share these things using mathematical software or the software WinPlot. Okay, so we consider simple equation dy by dt equal to y into y minus 1. Okay, so this is first order differential equation which is non-linear. So here what are equilibrium points? Equate right hand side to 0. So there are two roots, 0 and 1. Okay, so we call y1 star equal to 0, y2 star equal to 1. These are two equilibrium points. Now here Jacobian means we have one dimensional case. It is simply derivative f dash. So what is f dash at y1 star? F dash of 0, it is minus 1, negative. Only one eigenvalue, negative. So we can say that y1 star, that is 0, is asymptotically stable. Second is f dash of 1, it is equal to 1, which is positive. So we can say that equilibrium point y2 star, that is 1, is unstable. And you can see this figure. In this figure, the plots, solution plots are found for different initial conditions. Okay, so horizontal is time variable, vertical is y. Okay, we are sketching t versus y of t versus t. Okay, so if we consider initial condition at 0 or 1, you can say that solutions are straight lines, means steady state solutions. Okay, what happens in the neighborhood of 0? All the solutions in the neighborhood of 0 are tending to 0. That means 0 is asymptotically stable, which is found by using analysis also. And what happens with 1? If we consider solution of this system whose initial condition is in the neighborhood of 1, solutions are going away. Okay, so 1 is unstable. Okay, source. 0 is sink, 1 is source. Okay, here is second example of non-linear second order system which contains two equations. First equation is x dot equal to minus x, y dot equal to x square plus 1. So to find equilibrium, equate right hand side to 0. So first equation, if we equate to 0, we get x equal to 0. And so second equation also gives y equal to 0. So 0, 0. That is origin is 0. Now we find Jacobian of this function. Function is minus x, x square plus 1. Jacobian is minus 1, 0. So in first row we differentiate first function minus x. In second row we differentiate second function with respect to x and y partially. So this is Jacobian. If we evaluate at origin, then it is clearly a diagonal matrix with eigenvalues minus 1 and 1. So one eigenvalue is positive, other is negative. So it is saddle. This is phase portrait, that means solution trajectories. So we can say that some solutions are tending to origin and some solutions are tending away from origin. So this is sad. And now move to interesting phenomena, that is chaos. Okay, so if we consider differential equations or discrete systems, then we have some cases. Some solutions are converging to equilibrium point. Some solutions are diverging from equilibrium point, become unbounded. There are certain solutions which are oscillating. For example, if we consider y double dash equal to minus y, then the solutions are given in terms of and cos t, and these are oscillating solutions. Okay, so these are neither approaching to equilibrium nor becoming unbounded. Okay, so these are also there, neither unstable nor stable. Okay, still there are more cases. Okay, if we consider differential equation with order 3 or higher, then we can observe some more phenomena. Okay, so there are certain solutions which exhibit aperiodic or irregular motion. What is meant by aperiodic? Solutions are oscillating, but we cannot find period. Okay, so no repetition is there. Second thing is, these solutions are highly sensitive to initial conditions. Means slight change in initial condition results in completely different behavior. Okay, and these oscillations never settle. We cannot predict the future. So such solutions are called chaotic solutions. Okay, so this is history. I will not go in details again. I will share this presentation with coordinators. Okay, so of course chaotic solutions uh, should be found using numerical methods. Okay, so if the system has exact solution, then exact solution cannot be chaotic, because we have exact solution we can predict, and chaotic solutions cannot be predicted. Okay, no pattern is there. Okay, so numerical solutions are the important thing. So numerical solutions cannot be found using pen and paper. Okay, we need computers to find numerical solutions. Okay, so after the discovery of high-speed computers, these phenomena are observed. Okay, before that it was not possible. Okay, and chaos is completely natural phenomena. You can find chaos everywhere. Okay, our real life is best example of chaos. Okay, so we cannot predict the next thing. Okay, so I don't know what I will do after 1 hour. Unpredictable thing. Okay, so pattern is not there. Okay, what will happen tomorrow we don't know. How my friend will behave with me tomorrow, that I cannot predict. Okay, so it is not like that. So our life is completely chaotic. It is best example of chaotic dynamical system. So the meteorologist Edward Lorenz was the first person who observed chaos. What he was doing, he was observing weather. Okay, so in weather forecasting, he arrived to a differential equation. I will share that equation details. Okay, so the equation was third order differential system, which was non-linear system. Okay, of course, if system is linear, we cannot have chaos. The system was non-linear. He was solving that system, and uh, first when he solved, he get one solution. After some time, he solved once again the same system, but he was getting completely different solution. So he checked what was the problem. The problem was with decimal point in initial condition. For example, the first initial condition is 0.01 and second initial condition is 0.0100001. Okay, so very slight change in initial condition, but the result was completely different. So this is sensitive dependence on initial conditions, and we know that weather forecasting for long term is not possible. The system is chaotic. Okay, So chaos is observed in discrete dynamical systems, means maps, by Robert May in 1976. And this system was again a real life system. It was for population dynamics modeling. Okay. So there are some more systems which behave chaotically, like delay differential equations also. We discuss maps and differential equations, some particular examples. Okay. So the system discussed by Robert May was simple system. Let us see. Xn plus 1 is equal to Rxn into 1 minus xn. So this is a non-linear discrete dynamical system. Okay. So we can say recurrence relation. If we know value of x0, we can find x1 equal to R into x0 into 1 minus x0. Okay. Simple thing. Okay. When we find x1, we can have x2 and so on. Recurrence relation. Okay. So this defines population of next generation. Okay. We know that population of first generation affects population of next generation. Okay. Of course, this is simple model. We can have more complicated models because there are other factors also. Okay. This R is having physical meaning. It is called as growth rate of that population. It depends on species to species. So here we consider initial value to be 0.1 x0, and we observe different phenomena. Okay, so everything depends qualitatively on R. Okay, so there is qualitative analysis of discrete dynamical systems also. This is completely big course, so in one lecture I am unable to explain everything, but I have to give glimpses. Okay, so observations are like this. If R less than 1, okay, of course growth rate cannot be negative. For mathematics purpose it is fine, but for physical thing we take R to be positive. If growth rate is less than 1, then the population xn goes to 0 as n tends to infinity. And this is quite a natural phenomenon. Okay, so growth rate must be greater than 1. If rate is very small, then it must be steep. Okay, so here if we take R equal to 0.1 and plot these points, then we can find, okay, so this is first figure 4.1a, you can see. The population is tending to 0. Okay, so that species will extinct as we go on. Okay, so population cannot increase if growth rate is less than. Second case is we take growth rate between 1 and 3. Okay, so here it is observed that the population grows and after some stage it becomes stable. Okay, so initially there are a few oscillations. Okay, so R equal to 2.9. So these are called as transients. Okay, so initially you can find some oscillation, but after some time the solution is stable. Okay, so this is ideal thing, growth rate between 1 and 3. Okay, now if we increase the growth rate R equal to, for example, 3.25 and observe the population, then we can find that if we take x0 is 0.1, then x1 is 0.29, it is increased and so on. So after that we find out x17 is 0.8, x18 is 0.4, 0.8. Okay, let us see the figure. Okay, so you can observe that there are two values which are important. One value is 0.4952 and second value is 0.8124. So it is oscillating between these two values only. So let us see the figure. Okay, so if we sketch xn versus n, we can find that after some time these are oscillations. So it is called as periodic cycle. Of course, we can sketch xn plus 1 versus xn. It is called as curve wave plot. It is like wave of wave diagram. Okay, it is also showing the two cycle. Okay, So this square, final square, it is representation of these two cycles. Okay. So initially it was going to 0. After that, it was becoming stable. When we increase R to 3.25, it was showing periodicity, 2 cycle. What happens if we increase again? So for example, R equal to 3.53, we get 4 cycle, period 4. Again, if we increase R, then we get 8 cycle. Okay, so it is 2 cycle, 4 cycle, 8 cycle, and so on. So this phenomena is called as period doubling. And this, as we increase, our period will tend to infinity. What is mean by period is tending to infinity? We are not getting any periodic orbit. That means we are getting aperiodic solutions, and aperiodic solutions are nothing but chaotic solutions. So let us see. So here we have considered R equal to 3.53, and we can see that we are getting 4 cycle. Okay, so these 4 values are repeating. Then if R is 3.6, we can see that oscillations are there, but we don't have periodic oscillations. These oscillations never settle. Okay, and if we sketch xn plus 1 versus xn, we can find such figure, beautiful figure. This is called as chaotic attractor. Okay, so we don't have periodicity, and this happens with R equal to 3.6. And surprisingly, this really happens. This is physical phenomena, natural phenomena. So you can find such chaotic things everywhere in nature. Here is another interesting example in two-dimensional case. Okay, so consider similar two-dimensional system. Okay, it looks very simple. Xn plus 1 equal to sine of a into yn plus c cos of a xn, and yn plus 1 equal to sine b xn plus d cos dy. Here xn and yn are state variables. Okay, means we are in 2 dimension. N is our time variable, which is discrete. We give values 1, 2, 3, etc. So once we have x0 and y0, we can find x1, y1 pair, then x2, y2 pair, and so on. These are coupled things. Okay. Here A, B, C, and D, these are parameters. Okay. Surprisingly, for various values of these parameters, we get very beautiful figures which are called as Clifford attractors. These are named after mathematician Clifford. There is a nice book by Clifford which I will share in the last of this lecture. I will show you some figures. Okay, so here in this figure, horizontal axis is various values of xn. Okay, here we are getting pair for each n. We are getting xn comma yn a pair. Okay, so what I did, I found out 1 lakh values of this system using Mathematica software, and at each n we have a pair x0, y0. Then there is a point in this plane. Okay, x0, y0 is a point in plane. Similarly, x1, y1, x2, y2. Okay, and we consider A, B, C, D as 1.7, 1.7, 0.6, and 1. And we are getting this beautiful figure. Okay, so it is a nice exercise to change these values and get different patterns. Okay, so application of this chaos theory is not only in mathematics but also in arts, design also. Okay, here is another set of parameters, and we are getting this beautiful figure. This is third one set. This is fourth set. In principle, we will have infinite number of such beautiful figures. Okay. Now, I don't have sufficient time, so I'm moving to chaos in differential equations. So I need 5 more minutes. Sorry for that. This is the Lorenz system, which initially we talked about. So it looks quite simpler. Okay, so first equation is even linear. X dot is y minus x. Second equation, there is only one nonlinear term, x multiplied by z. And third equation, there is only one nonlinear term x multiplied by y. This sigma, r, and mu, these are parameters which are obtained by Lorenz in his system. And for various values, we can observe chaotic solutions. Sorry, is there any problem? Shall I stop here?
No, sir.
Excuse me.
No, sir. You can continue.
Okay, sir. Fine. Please mute if there is no any issue.
Yes.
Okay. If we sketch t versus x of t, y of t, and z of t, you can see these oscillating things. Okay, so you cannot find any beauty in the first figure, but instead, if you sketch x of t versus y of t as a parameter, you can find this beautiful figure. It is called as butterfly attractor. There is history behind this name, butterfly attractor. Search Google for this. So these are YZ phase portrait, XZ phase portrait. Okay, and this link, there is nice video presentation for this. Okay. Another example is again in real life. So this is by mathematicians Chua and Matsumoto. So it is in electrical circuit. Okay. It is containing only one nonlinear term g of x, and the term is actually piecewise linear function. It is not completely nonlinear system, and the solutions trajectories are like this. Okay, so this is Chua attractor. And third example, this is the last example. It is Rosler system. It is also famous system. Okay, so this figure 4.4 is Rosler attractor, and finally this is which is non-autonomous system. That means right hand side is containing t and it is second order. So this is chaotic attractor. Okay, so these are important references. First book, it discusses qualitative analysis of nonlinear systems. It is very nice book, and you can see various details. Okay. Then this is important paper by Lorenz, Edward Lorenz. This is important paper by May, Robert May. So these are first papers in the history. Okay, so these are celebrated results in the chaotic dynamical system. Okay. Few more references are also there. Possibly I will share all these details in the group also. Thank you. Now the session is open for discussion.
Thank you, sir. This was really nice session, and we received many comments about this session. So I have one question here. Can any differential equation have chaos behavior?
Of course, I have given examples. Maybe that question was before my that slide. I have given 5 examples of differential equations behaving chaotically.
Yes. And another question is how? 1 minute, sir.
Oh, no problem.
Maybe I lost this question, sir.
Fine. Next, you can take.
Yeah. Recent research scope by using numerical methods to solve this fractional.
Fractional, yeah. Okay. As we have seen, the nonlinear systems are not easy to handle. This is first thing. We cannot solve nonlinear systems using pen and paper. So we need numerical methods. Okay. Now, what is the importance of numerical methods in fractional differential equations? We have seen that fractional differential equations are not local. Okay. So non-local phenomena are there. So these are quite difficult to solve. Okay. And in general, for nonlinear systems of fractional differential equations, we don't have methods to find exact solution. Okay. Of course, if we consider integer order differential equations, routine differential equations which are non-linear. There are few methods for non-linear also. Okay, we have discussed such methods in BSc mathematics also, solving non-linear first order, second order systems, and we are getting exact solutions, but it is not the case with fractional. Okay, so numerical analysis is unavoidable with fractional case. Okay, now what is scope? We know that solving differential equation is easy task in numerical analysis, but solving integral equation is not that much easy. Why? Because finding derivative is simpler. So what is dy by dx at point 3? Dy by dx at point 3 we find using first principle as limit as h tends to 0, y of 3 plus h minus y of 3 divided by h. If we remove this limit and take h very small, then y dash of 3 can be approximated as y of 3 plus h minus y of 3 divided by h. What this means? We are having only neighbor values of y in the neighborhood of 3. Okay, so the values of y in the neighborhood of 3, that is y of 3 plus h, is sufficient to find y dash of 5 to approximate y dash. But it is not the case with integration. Okay, for example, you want to integrate y of t from 0 to 3. What you have to do? Remember Simpson's one-third rule, trapezium rule. You have to consider partition of that interval 0 to 3, and if you want better result, you have to consider very small step size. For example, h is equal to 0.01, and now how many steps are there between 0 and 3? This step 0.01. You can check that we have number of values and we have to compute all these things. So what are fractional derivatives? Fractional derivatives are integration of something. Okay, so finding integration is time consuming. So solving fractional differential equation is time consuming. So scope is find numerical methods which are good. What is meant by good numerical method? Which consumes less time and give less error as well. I think I have answered that question.
Nice. Sir, I think you don't have any questions.
No problem.
Yes. And some students, they are asking for the PPTs. So is it
yes, of course.
The PPTs?
I will share PPT as well. PPT is there.
Yeah, sir. Yeah, we can share. Thank you, sir.
Thank you.
So should I come to the sum up, sir? Yes. Now I request Mr. R.D. Shinde, sir, to propose the vote of thanks. Shinde, sir, please.
Okay. Hello all. I am thankful of Dr. Sachin Kumar Bhalikar, sir, for explaining this, for giving this nice lecture. Sir has explained qualitative and quantitative analysis of systems, stability analysis of continuous dynamical systems, and